All right, our final topic for this section on probability generating functions is what's called infinitely divisible distribution. So it's an interesting family of distributions which has this special property called infinite divisibility, as I'll define now. So we call a distribution infinitely divisible we'll say the distribution F is infinitely divisible if for every n, okay, for every integer n, there exists an IID sequence, so x1, x2, up to xn, that are IID, such that the sum Sn of those NIID random variables has distribution F. So in other words, I can decompose any random variable. So if a random variable has a certain distribution, if that random variable is infinitely divisible, I can express that random variable as a sum of IID random variables, of any number of IID random variables. So let's some distributions have this property and some don't. So let's see some examples. So the degenerate distribution is just the one that assigns probability 1 to a constant. Is this infinitely divisible? Well, can I write a constant as a sum of arbitrarily many IID constants or identical constants? Well, yes. For each n, I write x equals c over n plus c over n times. And this is, of course, equal to c. So I can write, so if I take those n constants, and I can do it for any arbitrary integer n, then I'm in business. All right, Poisson. Say that x is Poisson with parameter mu. Remember then, we already know that by the reproductive property, if I have any n, and I define x1, let's call them y1 up through yn to be the Poisson mu over n, then their sum is Poisson with the sum of the intensities. Then the sum y1 up to yn is Poisson, and their intensity is the the sum of the intensities, mu over n plus mu over n times, so it's mu. So that's infinitely divisible. How about the negative binomial? So the negative binomial has an interesting property that I want to talk about to wrap up this section. So something about the negative binomial, remember in when we introduced the negative binomial, we talked about it as the number of trials needed to achieve the rth success. So it's assumed that if we're choosing an rth success, that it requires that r be an integer, right? So recall our interpretation. So it's the distribution of the waiting time until the rth success in repeated tosses of a p coin. And so with this interpretation, so this interpretation required p to be between 0 and 1 because it's the probability of tossing a head and a p coin. And r needed to be an integer because we can't have a fractional success. But remember, we wrote multiple different versions of the negative binomial. They're all mathematically equivalent, but where the name negative binomial comes from, one of those ways of writing the mass function was with a negative in the binomial expression, right? So we have negative r, choose k, p to the r, negative q to the k, okay? This is when x counts the number of failures until the rth success. Okay, so if that's the case, we actually have a little bit more that we can work with here because note that negative r, choose k, is negative r following factorial k over k factorial. K is an integer. And so negative r doesn't have to be an integer for this to make sense. Right? Because this is negative r minus 1, all the way down to negative r minus k plus 1. So this is well defined, even if r is not an integer, right? So what we can do is let's let r just be any real number. Then we can actually write the Taylor series expansion of 1 minus q to the minus r. So it's 1 plus minus r times minus q plus minus r minus 1 times minus q squared. It's over 2 factorial, etc. And we can write this as a sum k equals 0 to infinity of minus r choose k minus q to the k. Okay. So we know that 1 minus q, right? 1 minus q is equal to p. Okay, so if I multiply this up here by p to the r times 1 minus q to the minus r, the minus r's cancel and we get p to the r times p to the minus r, so we get 1, okay? But we can also write this as p to the r sum k equals 0 to infinity minus r choose k minus q to the k. So what that tells us then is that this expression up here, star, right, is a probability distribution for any r bigger than 0. So what does it need to be a probability distribution? It needs to be non-negative for all. It needs to be non-negative, and it needs to add up to 1, and that's what it does here. Okay, so we still have our same expression. We still have our same relationship that if we have a negative binomial random variable, x, by definition, its generating function is expectation of z to the x so it's the probability mass function times z to the k. We can throw the q, we can put the q and the z together, and we get minus r choose k, p to the r, qz to the k. So we can express this as p to the r 1 minus qz to the minus r. And this is equal to GW of Z raised to the power R, where W is geometric P. We've seen this already. But what's the consequence of that is, well, whenever we have a generating function that is expressed as the power of another random variable, then we have infinite divisibility. Why? Because what we can do is we can express x as a sum of y1 up through yn, where what we do is y1 up through yn are going to be IID negative binomial p and r divided by n. If r is bigger than 0, then r divided by n is bigger than 0. So it's a valid distribution. Doesn't have the interpretation anymore as the number of failures before the first success, but it's still a valid probability distribution, as we showed. And we still can calculate its generating function in just the same way. And it's the generating functions of all of these are g w z to the power r over n. And we have n of them. We're going to raise them to the power n. So we're going to get gwz to the power r, which is the generating function of the negative binomial PR when W is geometric P. So that's a little precursor. I mean, here we talked about probability generating functions, which are mostly relevant in the case of positive random variables, and in particular, really, when we're talking about discrete random variables. We can define similar things in more generality, and we will, but we see that there's some pretty easy calculations we can do with the generating function that we couldn't do otherwise. So it's a case where we actually have, in some sense, we've introduced a relatively complicated object, or a seemingly complicated object, this expectation of z to the power x, but we did it for a reason. And in doing that, it made a lot of things much easier. Okay, so we'll come back to the idea of generating functions later on. We'll talk about moment generating functions. But our next topic now is to move away from discrete random variables, and we're going to move into continuous random variables.